So
So good morning, everyone. First off, thank you for attending and taking time out of what is an active weather day across the Eastern region to be with us this morning. For those of you who may or may not know me, my name is Jordan Rabinowitz. I'm a meteorologist within the NWS Eastern Region Scientific Services Division. Welcome to this webinar on the experimental NWS HeatRisk product suite. During this webinar, an overview will be provided on this exciting new tool with an Eastern region focus. We'll also look at how HeatRisk works, how it can be used, and we'll look at some verification as well as additional resources available to you and your partners. With that being said, I'm now going to hand the floor over to Kim McMahon. Kim, the floor is yours.
thanks, Jordan. Morning, everyone. I'm Kim McMahon, National Weather Service Public Weather Services Program Manager, former ERH Tropical Marine Tsunami Program Manager. Today's webinar is going to be recorded, and by attending, you consent to the recording of your likeness. After the webinar, the recording is going to be available on our public program Google Sites at the URL shown under the second bullet. So please keep your lines muted until the Q&A at the end. And with me today is Mike Stonemeyer, who is the Division Chief of the Western Region Headquarters Science and Technology and Fusion Division. Mike and his team developed the initial approach to HeatRisk in 2013, and he continues to lead the development with the latest release. And while we'll focus on experimental HeatRisk in this presentation, I just want to remind everyone that this is another tool in the toolbox of weather service forecasts to assess and message forecasted heat. So with that, I'm going to hand it over to Mike.
All right, thanks, Kim. Can everyone hear me?
Yes.
All right, great. All right, since most of you have some understanding of heat risk through either taking the training or looking at VLab or hopefully looking at the public page from Western Region, I'll review some of the high-level aspects of heat risk philosophy and the 5-tier structure, but I'm really not going to take a lot of time to dive too deep into that, so we have time to walk through some of the more interpretive services and use of the heat risk forecast, why we did what we did, those kind of aspects. So heat risk is a color and number-based framework that compares the forecast temperatures against scientifically derived thresholds, and that provides us with an index of the potential risk for heat-related impacts. When we developed it, we wanted it to be easy to communicate, like the air quality index or UV index, which expresses complicated information in an easy-to-understand approach. And as we'll talk about, the science going into heat risk is pretty complicated. I want to reiterate that heat risk itself is a framework. So if the underlying science needs to be tweaked a little bit or modified down the road, without compromising the simple color and numeric messaging approach, we can do that. So when we started developing work, we did a lot of peer literature review looking for nationally valid heat health findings. Those could inform our approach when we developed heat risk. So for example, research showed that communities adapt and build to their local climatology. So we built in 2.5 kilometer resolution climatological information. Research showed us that acclimation occurs on a time scale of a week or two. So we've created thresholds that change over that time scale, similar to how the normal climate curves change at each location. Research has also shown that there's some level of heat that's physically dangerous to the human body no matter the time of the year, but it also suggested that everyone has different heat tolerances. So this means that a single threshold isn't going to work for everyone. So we build a 5-color and number system into the approach to provide information specifically for a variety of heat tolerant groups. So research also shows us that the use of the 95th percentile of temperature to identify heat episodes in a particular location are excessive for that location. You can define it to be that way. And that's a common approach that was used at the time in quite a few studies we looked at, and also in several heat health warning systems around the world. So that's what we leveraged as well. Because of the desire to have high resolution output that's still skillful out to 7 days and beyond, we base the system on temperature, since temperature is the first order driver for heat impacts, and we have the most station observation data sets available for temperature. We recognize that other items like wind, humidity, and clouds are important secondary drivers, but there's quite a few obstacles in our way to use them directly. First, there's no 2.5 kilometer daily wind or cloud climatology grids available to generate what is unusual for an area. And there's not really solid national rules on how to apply wind or cloud adjustments to heat for heat risk. Second, we just don't have that many official weather stations that report routine dew point temperatures with a period of record that goes back 30 to 50 years in order to calculate a skillful 95th percentile of heat index. Even our ASOSs don't have a 30-year period of record yet. Third, forecasting hazards like wind, dew points, and clouds are pretty challenging beyond a short-term period, and that also limits our long-term skill. So while these weather elements are important, we recognize that the most skillful parameter we have that we forecast for are temperatures. We're pretty good at forecasting temperatures out through 7 days, and that really drives the bulk of negative heat impacts. But we can, however, roughly estimate humidity and air mass characteristics by leveraging temperature ranges and minimum temperatures. The last thing I'll mention here is that in order to be consistent across the CONUS, the same framework rules have to be applied in a similar fashion to all locations. While any method can be tweaked to be better for one particular location, a national approach can't have local rule sets imposed within it without the heat service becoming inconsistent. So here you can see the factors that are considered in the heat risk approach. Both high and low temperatures play a role in predicting the 24-hour value. The thresholds identifying the various levels of heat stress change through the year based on local climatology to better account for acclimation. The entire 7-day period is examined to identify periods where excessive temperatures exist for 2 or more days. The likelihood that accumulated heat stress generated during the daytime would be mitigated or maintained overnight. And HeatRisk is the first national scale high resolution US heat forecast tool to actually incorporate real national heat health data within it. And that informs us as to what temperatures are at the levels that pose an elevated risk for heat related health complications. All right, so this isn't my particular area, but we need to talk a little bit about the CDC heat health relationship data. While the roots of heat risk began as a purely climatological framework in 2013, in 2018, we began working with the CDC to incorporate actual heat health impacts into the approach. The CDC has access to not only peer-reviewed heat health modeling approaches that are state-of-the-art, but also to national data sets that would be needed for the approach. After initial proof of concept testing, looking at both mortality and morbidity data relationships, we settled on using mortality data because at that time, this was really the only heat health data set that was available across the CONUS, all the states at the county level. Using this list of available counties, we provided the CDC with the best observation station with continuous daily data from 2004 to 2018 within each of those counties to base the relationship on. This provided us with around 700 city-county pairs ranging from large urban areas down to rural locations. I don't have time to get into the specifics of the epidemiological methods, that's a tough word, that were performed, but these are considered state-of-the-art methods within the heat health community. Mortality-based exposure response profile curves were generated for both max and min T. Air pollution, seasonality, long-term trends, and day of the week were just some of the parameters that were controlled for in their model. Lastly, health impacts were estimated for a cumulative lag period to account for the delayed effects associated with heat exposure. A second stage of modeling was needed to iron out stability issues, especially in areas that were affected by sample size issues. So think of the second stage modeling as a way to smooth out the imprecise exposure response relationships due to the sparseness of data in some places. The bottom line here is that this approach to generate these relationships is far superior to what we could do by just simply collecting mortality data statistics from local hospitals and basing relationships just on those limited data sets. So here's an example of what a temperature mortality relationship for a single county city pair would look like. So briefly, the y-axis denotes health risks and the x-axis denotes temperature. The area to the left of the blue no risk zone where the effect of heat is not observed. The area to the right of the blue vertical dashed line is the heat sensitive risk zone. That's what we're going to be focusing on. The yellow dot represents the minimum mortality temperature. This is the temperature at which the effect of cold is not observed and the effect of heat starts to increase. The gray area represents model uncertainty. So both warmer and cooler climates could have similar shaped relationship curves like you see here, but underlying underlying exposure patterns and the resultant heat attributable death characteristics can be totally different. In hotter climates, we may see heat attributable deaths increasing with increasing temperatures. That's a relationship we all want to see. But realistically, in cooler climates, extremely hot temperatures are much more rare, so that heat exposure occurring at moderately hot temperatures could actually result in greater adverse health outcomes overall when you bin all of those up into temperature ranges. So the CDC combined the heat health risk information with person days of exposure, and that developed this distribution of heat attributable deaths over a range of temperatures, which are represented by the bar graphs here in this particular example. Note the difference in characteristics between the left side in a warm climate and on the right side with a cooler climate. All right, the final step was to translate all of this epidemiological analysis into actual values that the Weather Service could use in a heat risk approach. Ultimately, the metric we settled on was percentage of heat attributable deaths, or FAD. This metric provides us with a range of percentages that total up to 100 between that minimum mortality temperature and the maximum temperature observed at the station. From that distribution, it was just a mathematical exercise to derive the specific percentile temperatures that you see at the bottom, which are used in the creation of the heat risk thresholds. All right, so let's jump into those 5 heat risk categories using the approach. So the worst category is the extreme level. It's colored magenta, numbered level 4. I'll let you read the full text here, but the main takeaway is that this level is triggered when afternoon temperatures are very near or above all-time record values, or it'll be triggered when there's 2 or 3 consecutive days where both the maximum temperature and the minimum temperature contributions are all in the red category. We trigger it on 3 days for warm climates where heat is more common, and on 2 consecutive days in cooler climate where long duration heat waves are less common. The next category is the major category, colored red and numbered 3. Again, I'll let you read the words here, but the important takeaway is that there really isn't much difference between magenta and red days. Both magenta and red level events represent something in that top 5% of hottest days and nights in the climatological reference period for that location. But either the duration criteria or the extreme maximum temperature criteria weren't met for the red criteria to be augmented to magenta if we're in that red category. But it's important to remember both categories are very impactful. I'll just make a few points about the orange category on this slide. So this category will primarily negatively affect those populations and sectors who are in that at higher risk category. It's important to keep in mind that most of us go from air-conditioned cars to air-conditioned work, their gym, the home. And so we'd view these days simply as warm or uncomfortable. But since we stay hydrated and cooled, we really aren't that much at risk. But those populations who are unable to take those preventative measures or are just more sensitive to heat would potentially be impacted by the lower temperatures that orange would indicate. It also is important to realize that even those of us who aren't normally heat tolerant we can actually become one of the at higher risk populations when we don't adequately hydrate or stay cool during the heat of the day. I'm talking about things like attending an outdoor venue or participating in strenuous activities outdoor without taking proper precautions. We see this many times when we have heat exhaustion or worse occurring at outdoor venues or sporting events during the summer on orange days amongst otherwise healthy individuals because of this. So I put all of the threshold generation review on this slide. I'm going to assume the vast majority of you have already heard about how we derive them, but I'll review it briefly on this slide. So this chart's something that's available to all the CONUS WFOs as a visual means to see the daily thresholds for the entire year. This example is for Max T for Washington Reagan National Airport. The x-axis denotes the months of the year, and the y-axis is temperature. The black stair-step curve denotes the daily NCEI 1991 to 2020 normals for this location. The lighter gray stair-step curve denotes the smooth 95th percentile curve derived from a standard period of 1970 to 2020, a 51-year period. The dots on the map represent the daily record high temperature for this station during the entire period of record. The yellow line is based on that minimum mortality temperature that we just talked about, where the effects of heat begin to occur. For rural locations, we utilize the first percentile temperature in order to have a slightly higher temperature to represent those more resilient populations that generally live in rural areas. Moving to the red curve, the flat part of the curve is derived from the 50th percentile of CDC heat attributable deaths. So this represents a temperature where 50% of the mortality was modeled to occur at or above this value. So an even more important thing to keep in mind is that 50% of the modeled mortality occurs at cooler temperatures than this. We chose this intermediate value to not overwarn, but still provide good values that would make a positive difference to meeting our Weather Service mission of protection of lives, property, and enhancing the national economy. When this threshold encounters the 95th percentile curve, the daily red threshold is then going to follow that curve upward and then back downward. And that's our way of acknowledging acclimation amongst heat tolerant populations. The orange curve is an intermediate value between the red, yellow, and the normal curve. The orange portion of the chart represents lower temperature values that would still be of danger to those at higher risk populations and heat sensitive sectors. We also provide an acclimation aspect to orange. Those are the stair-stepped areas, but we cap that acclimation value at the CDC 50th percentile value or the red shoulder value, because it's likely that many of the heat deaths that occur in the summer continue to be within this at higher risk population. The fall shoulder flat area of the curve is higher at many locations to represent the more resilient population that remains after the heat of summer. This value utilizes the 25th percentile of heat attributable deaths from the CDC threshold data. So again, this really sounds complicated, right? But heat is pretty complicated. So hopefully you'll appreciate just how much heat health science actually is considered in this approach. It isn't just looking at max and min T's and just throwing out, some values. There's a lot of science that goes into this. So at this point, we've defined all of our daily thresholds for this example location. And as the example chart shows, on any given day, this location has unique daily thresholds for yellow, orange, and red, which can then be used to put the forecast temperatures into a heat-related context. So for an example, on July 15th, the yellow threshold would be 72 degrees, the orange threshold would be 91 degrees, and the red threshold would be 98 degrees. All right, so we follow a somewhat similar approach for minimum temperatures, again, leveraging the CDC data, but this time we only use it for the yellow threshold. We solely leverage climatological data for the orange and red thresholds. This is for two reasons. The first is because the CDC didn't find as strong of a relationship between our health data and minimum temperatures independently for us to use our modeled thresholds exclusively. So we use the minimum temperatures to identify those situations where climatologically unusual overnight heat is contributing or maintaining or even increasing the heat stress that's accumulated during the daytime period. Or if cooler minimum temperatures would lower, that increased heat stress. The second reason we include minimum temperatures in the approach is because we can leverage the general correlation between elevated humidity and elevated minimum temperatures, which we all know that's a core concept of Meteorology 101. We leverage this relationship in a few different ways in a heat risk approach. So one area we do this is by lowering the red spring and fall shoulder values, those flat red lines on the minimum temperature curves, in more humid climates, and we actually raise them in more arid climates to better account for the role of humidity. All right, so we carry the same process out across the CONUS to calculate the max and min temperature thresholds at about 3,100 individual stations where we have high quality, long duration, and consistent climate data, which have passed our QC process. We then use the PRISM high resolution climatology grids with this point data to develop daily gridded red, orange, and yellow thresholds over the entire CONUS. So this science-based approach leads to very different annual threshold curves at each location, and that's what we want. Here you can see an example for both the Raleigh-Durham International Airport on the left and downtown Los Angeles on the right, showing how these thresholds increase during the spring, they peak, and then they drop during the fall. But the values and even the curve shapes themselves are very different in order to represent that climatology appropriately. All right, the big question. We know humidity plays an important, though secondary role in heat impacts, especially across the eastern US. In fact, there's strong evidence to support the 100th meridian as a natural divide between the humid east and the arid west, as shown in vegetation and rainfall. That's also true for peak average dew point. So we have compelling evidence to support making different moisture adjustments within the experimental heat risk algorithm for locations east and west of that divide. And that's just what we do. We split the country up into either a humid east or a more arid west. So let's dive into the humidity accommodation just a little bit more, as I know it's a huge concern for you all out east. The heat risk algorithm leverages a term we call the diurnal range modifier, or the DRM, which is simply the highest daily maximum temperature in the annual curve minus the highest daily minimum temperature in the annual curve at each location. We calculate this value at all grid boxes, and locations with humid climates exhibit a smaller DRM range. Heat risk leverages this natural humidity divide line in the middle of the country and these DRM values to define the area where we'd apply one of two 24-hour equations. Within the transition zone between 104 west and 97 west, we define the area where the DRM is less than 27 degrees to utilize the humid heat risk 24-hour equation. Areas where the DRM is greater than or equal to 27 degrees would utilize the dry heat risk 24-hour equation. So all areas west of 104 west would also utilize the dry equation to keep it all the same. And all areas east of 97 west would utilize the humid equation. After filling in some islands in the transition zone, this results in a meandering border within a transition zone that roughly approximates that transition between moist and more arid climates that was recognized well over 100 years ago. So as mentioned earlier, we also use that DRM to adjust the red minty shoulder threshold values up in more arid climates and down in more humid climates to again provide a better approximation of humidity in the approach. All right, so let's talk about how we created the overall 24-hour value of heat risk, and that is the final output of the approach. So first we assign a 0, 1, 2, or 3 to the individual max T and min T forecast temperature values based on where they fall within the daily red, orange, and yellow thresholds for that location. So if it falls in the red category, we assign that pixel a 3 for the max temperature contribution. We then combine those values coming from the morning min T, the afternoon max T, and the following morning's min T to create the 24-hour value using one of two equations. For humid climates where humidity plays a significant role in modifying the feel-like temperatures, that combination involves having the minimum temperatures on either side of the afternoon high providing 55% of the overall 24-hour value. The contribution for the afternoon high accounts for the other 45%. In dry climates, the impact of heat stress from the afternoon temperatures is generally much more substantial than that from humidity. Therefore, the contribution for the maximum temperature gets the greater weight, in this case, 67% of the overall 24-hour value. The minimum temperature provides the other 33%. We apply a bit more logic to fine-tune that final 24-hour value, especially out east, to again better account for humidity, and then we round it off, and the integer value is the final result. All right, let's go through a couple of quick examples working through the 24-hour equations. So let's focus on New York City Central Park for this. First, we can demonstrate that the time of year matters. So in this example, the heat index is 95 degrees for both June 1st and July 15th. The high and low temperatures are exactly the same, obviously. But in this early part of the year, we see that the lows of 72 and 73 would both contribute a value of 2 to the 24-hour equation, and the high of 94 would contribute a value of 3. So if we apply the ratios we described on the previous slide, a 24-hour heat risk value of 2.45 is calculated, which is very near the upper portion of the orange category, since we round values of 2.5 and higher to be colored red and to be assigned an integer value of 3. So we're in that upper orange category. So because this is an early time of the year and the max T value is in the red category, heightened messaging or perhaps an advisory would be warranted. However, using those exact same values, again, same heat index value as well, in the middle of July results in a yellow 24-hour heat risk value of 1.45, which essentially is indicating that these temperatures aren't really that unusual for this time of the year in that location. So you can see that heat risk takes time of year into consideration to place the heat that's observed into climatological context. Now let's look at how the role of humidity can be roughly accounted for in the approach. So let's say that on the 17th of July, a bunch of moisture moves into the area and the dew points increase into the mid-70s. So now our overnight lows stay elevated at 77 degrees, and the daytime high will keep the same as it was on the 15th in that previous example. Now when we plug in the contributions from min T of 3 for each of those values and a 2 still for the maximum temperature contribution, we get a non-rounded 24-hour heat risk value of 2.56, which is in the red category. This is much higher than what was obtained when the heat risk value was 95 just a few days earlier. In this case, a calculated heat index value for this situation resulted in a value of 105. So hopefully you can see that heat risk is sensitive to higher dew points and humidity through the use of the minimum temperature contributions. It's not exact one-to-one, but it can account for it in a bulk kind of manner. All right, so let's step back. Let's look at the full process real quick. You should now have a pretty good understanding of the broad strokes of what goes into heat risk, how it works, the thresholds. In a nutshell, we use those CDC heat health relationships. We use local climatology to generate data at over 3,000 points. We then use PRISM to develop 2.5 kilometer daily grids for the yellow, orange, and red thresholds for both max T and min T. And then those daily thresholds are compared to the NDFT temperatures at each grid box, with a max T and 2 min T integer contributions going into one of two equations. This results in a daily 24-hour experimental heat risk grid for the 7-day period. All right, so since heat risk was initially developed in the West, I always get questions, so how does it work elsewhere? So as you know, heat risk was developed using mortality data thresholds. So with heat risk going CONUS-wide, we wanted to test the approach using independent data over 5 full heat seasons to generate long-term verification. So in this case, we examined CDC-provided emergency department heat-related injury data, which in this example is expressed as a rate per 100,000 emergency department visits overall. So these data are organized into 10 regions across the continental United States based on FEMA regions. For each of those regions, the daily heat injury data counts are compared to the daily average observed heat risk values using all of our approved NCEI points in each of the FEMA regions for the full heat seasons from April through October 2019 to 2023. So you can see that each FEMA region has its own chart plotting the data. I know you can't see the numbers, or probably not even the dots that well, but we put in a logarithmic correlation with FEMA region 10 in the upper left and FEMA region 1 in the upper right. The center map shows the date with the highest impact rate over that entire 5-year period, which occurred on June 28th, 2021, when the Pacific Northwest suffered from a historical and devastating heat wave, and the Northeast US had a significant heat wave occurring concurrently. So what are the results? So in the weather and climate world, we pretty much get excited when we see correlation scores above 0.6. These 5-year correlations between heat risk and an independent injury data set across all regions were well above that, with the lowest correlation score being 0.80 in FEMA Region 1, which is the Northeast area up by Maine, and the highest correlation score being 0.9 in FEMA Region 6. 5-year correlations in all of the FEMA regions within Eastern Region were between 0.80 and 0.89. So this is a great indicator of the utility of heat risk, not just for the big warning days, but also for those other times when less widespread but still important heat-related impacts are happening. Is it perfect? No. But this independent data set does show that heat risk did quite well over a 5-year period over the entire country, not just in Western Region, in identifying the bigger events in the regions. It also shows that even without directly utilizing a heat index, it provides a skillful means to identify the days when many people were going to emergency rooms for heat-related injuries, apart from those other less impactful days. All right, so let's get into some tools. So there's several tools available to the local meteorologists in the form of grids within the local GFE. One of these is the product recommender, which provides a zone-based recommendation to issue a heat product or to consider the situation more closely for the potential of issuing a product based on the mean 24-hour heat risk value in that zone. We've been using this approach in the Western region for over 5 years now. These recommendations are based on utilizing those pre-rounded non-integer results from the 24-hour equation, leveraging those values between 2.0 or the mid-orange range up to 4, the magenta range. The entire range of orange heat risk are not utilized in making a product recommendation or consideration, as that would lead to product fatigue. So we just use that upper half of the orange and the upper half of that half of the orange essentially for advisories. But heat risk will likely make more recommendations for action than our traditional thresholds because it is enhanced on looking at that more at-risk populations and including them within our products essentially. So also within a GFE are Hill Max T and Hill Min T grids. Those essentially are those gridded integer individual contributions that are going into the 24-hour equation. So these grids allow you to see a bit into the process prior to that final outcome. In Western region, we found that these grids help a bit with interpreting the final heat risk value and also for tailoring your heat messaging. For example, we'll frequently include messaging, all of us, to move activities to the cooler part of the day, or that the use of fans and opening windows at night will be adequate. Those are some of our traditional call to actions. But if the Hill Minty grids are red, this indicates those temperatures are something, again, like in the top 5% of the warmest nights at that location. And those actions will probably not be adequate to reduce the heat stress built up during the daytime. But if those Hill Minty grids are yellow or orange, then that type of messaging is probably going to be pretty appropriate. All right, so let's talk about this consider recommendation I've talked about a bit. Because impacts can and do occur with just a moderate or orange 24-hour value, we found that heightened messaging or even the issuance of a heat product could still be warranted. This recommendation is provided, this consider recommendation is provided to the meteorologist to consider other items in their decision. Is it early in the season? Is this an area where we have less air conditioning use? Is it occurring over a weekend with large outdoor venues going on where there's going to be more people put into that heat vulnerable population group? Is this just a brief cool down between two excessively hot periods and we should bridge that slight decrease in temperatures with a product, because we have that known lag factor of heat impacts, and also it just keeps the overall heat event intact. Are there widespread power outages in the area? Are heat indices high enough to warrant issuing a product to provide enhanced messaging even at this orange level? This is what should be considered when a product recommender grid is providing that consider recommendation. So as an example, the benefit of including heat risk in a heat Wawa product process, I provided a 7-day loop of daily heat risk values forced by day 1 NBM values during a significant heat wave in August of 2023. That's on the right-hand side. So the white polygons are the National Weather Service's heat products issued independently using a heat index approach. While every week last summer didn't show this type of good matching, many weeks were pretty similar in behavior where our Wawa heat products were issued in areas of the orange, red, and magenta heat risk. So as mentioned, heat risk wasn't specifically developed to reproduce heat index thresholds or to only support the issuance of our traditional heat products. The use of heat risk with heat index knowledge should ultimately be used together to make the best heat messaging decisions. But heat risk does do a fairly good job in identifying those higher heat index days to occur within the higher half of the orange category and into the red and magenta categories. So I'm going to illustrate this a different way. So let's look at one of those climatological charts that are available to the local office. That's the one in the upper right portion. These annual charts show each observed max T and min T observation value for a year, colored based on their integer contribution to the 24-hour equation, and it's annotated as a dot for the max T and as a star for the min T. At the bottom, you can see a strip chart. That color, those colors are the 24-hour values, all kind of linked together in that strip chart. In the upper right-hand corner, we've provided what the algorithm would have generated at that location for heat product recommendations. So this example is from Boston Logan International Airport for 2021. And you can see the list of dates where heat products would have been recommended, along with a handful of dates that the algorithm would have recommended that the meteorologists consider other factors to determine the appropriate action. The bottom chart, that one isn't available to you, came from our development activities in 2022 when our big focus was really tuning heat risk to better approximate those big heat index days. So that chart has a normal curve of daily heat index in blue, a 95th percentile curve of heat index in black, along with a daily, hourly maximum heat index values as dots, and we colored those according to various heat indice ranges. So the top 10 box provides the dates and values in 2021 of the top 10 heat index days for that year. So I'll leave it up to you to cross-reference the two, but heat risk has the majority of dates of observed high heat index within its recommendation and considered date ranges. While we picked this one example to show you, we observe this type of relationship generally at the other 20 Eastern US sites that we used for this development activity in 2022. All right, so it's going to be challenging to verify heat risk locally. I know we get a lot of people that want to take a local heat health impact data set and then do some verification with it. Since the approach really is focused on identifying those top level heat events using a 95th percentile approach, at the basic level, heat risk pretty much will verify as well as the temperature forecasts do. So one common issue that we do see in heat risk forecasts is an under forecasting at longer lead times. And lots of times this is due to the conservative nature of our forecasts as we get into the extended period. While we tend to spend more time on maximum temperatures and have pretty good skill with those out to 7 days, we sometimes do tend to underestimate how warm the overnight mins will be, and that can have a pretty big impact on the heat risk forecast itself. When you drill down to local and county level data sets, some of those impacts aren't going to be nice and linear and well aligned with heat risk. Overall, I think it's pretty unfair to expect any national approach to work for any and all user groups and impact data sets that we can find. So expect to see some data sets in locations where the data don't line up perfectly with increasing heat risk. You saw in the CDC modeling section how some areas have more heat attributable deaths occurring at cooler temperatures versus the very hottest. We also see that kind of behavior when we compare winter road accidents and snowfall. Many more accidents happen on lower snowfall threshold days than at the extreme major storm values. So the bottom line is that impacts due to any weather hazard are intertwined with many other human and societal factors that make the data sets more messy to deal with as they get more localized. That's why we verify heat risk with national data sets when possible, to get the big picture of how it's verifying. The example graphics on the right illustrate two very different results when you do compare a specific local impact data set with a station-based heat risk climatology. In the upper right, we see a near perfect relationship between increasing heat risk categories and total impacts occurring in each category. That's great, right? The bottom right figure, though, is different. For this particular impact data set, the majority of impacts occurred within the orange category. We can't really know the reasons for this type of behavior, but it doesn't automatically mean that heat risk doesn't work in the area, only that for this particular impact data set, there's a different relationship between the impacts and a method that leverages a 95th percentile type of approach. The decision maker still has very valuable information here. They can take action on orange heat risk days in the future and mitigate that impact in the category where it matters most. For whatever reason, the impacts tail off with increasing heat risk values, and it's going to be hard to identify why that may be. A visual consideration with heat risk is there's going to be artifacts. There's artifacts in all of our gridded data sets. None of it's smooth and perfect. So we're all aware that PRISM has its own artifacts, such as including non-representative or BRAD observations. It has different details with regard to how it represents terrain, thermal belts, lakes, etc. IRMA and RT may certainly have their share of artifacts. I think we all know that, right? All of those are going to feed into the NBM, resulting in issues like cold water values over the lakes and water areas, bullseyes where bias correction of bad or non-representative observations are occurring, and of course that METAR location pixelation issue. Speaking of observations, we have to deal with missing data, station moves, urbanization, land use changes, and so on. Those are also going to lead to artifacts when you place those observations into a gridded analysis. And last but not least, the heat health data that goes into this approach has its own variability based on, again, how the population responds to the heat in their area. And so we're going to have representativeness issues and variability issues to deal with within a gridded approach. So in short, all of this, unfortunately, is going to lead to some pixelation and artifacts within the approach. So in addition to those artifacts that are challenging to mitigate, we also need to acknowledge that when you combine 3 different weather element grids together and incorporate heat health data into it, you're going to have some blobby and non-smooth behavior at times. But realistically, we deal with all those issues all the time within our other gridded analyses. So we should give heat risk some grace when it comes to the output. When we look at heat index grids, we see that those fields are also blobby and they contain bullseyes and islands. In the example at the far bottom right, maximum heat indices range from 103 to 131 across even this limited domain in Texas. So even our heat indices fields are neither continuous nor uniform. In the West, where heat risk has been available for almost 10 years now, partners are relying on heat risk more and more. Some states like California actually are leveraging heat risk within their decision processes. They put their KML files of the daily heat risk on their internal dashboard. Media partners are picking up on it. They use it in their broadcasts and in their social media channels. Health partners are including it in their own briefings and distribution lists. Heat risk is in planning documents. As you can see, there's examples from Maricopa County's Hazard Mitigation Plan and also the California Governor's Office of Emergency Services. Schools are using it to inform their decisions on outdoor activities. Speaking of schools, wet bulb globe temperature is obviously another important tool in the tool chest when it comes to those specific activities outdoors. We're not saying wet bulb globe temperature isn't useful as well, but that along with heat risk, again, provides you with probably a more holistic message for the schools. So the simple color number system, when we ask people, why do they like heat risk? It's really that simple color number system, along with the lack of geopolitical borders, that really have been identified as the big reason that the partners really do like it. So the heat risk service is more than just a 7-day forecast. To help support our partners, along with providing that valuable background information for us, the meteorologists, because we got to get comfortable with this, right? The heat risk service also provides a wealth of heat risk climatology information going back to 2005. So via the webpage address provided at the top, the main map and the pull-down menu in the upper right allow you to access this information. It's important to state that this information is most useful when working directly with partners and used to acclimate yourself to how heat risk has performed in the past. We highly recommend that you don't just blast out an email with this link to all your partners as soon as you install heat risk, as the information on this page is pretty science geeky, and it's probably going to generate more questions and solve answers if you just put it out there cold and you're not there to help interpret it. That's the big reason this page isn't directly linked on the public page, but instead we set it up so you can access it by just typing in /historical after the public webpage address. So I've mentioned these annual charts before. Those, along with the MaxT and MinT daily threshold charts, like the one from Washington Reagan that we talked about early on in the presentation, those have been shown to be of great use when we work with partners or when we get more acclimated to the approach. So annual charts like this one for Philadelphia International Airport easily identifies early season heat around the 1st of June. But the most impressive heat event occurred between the 19th and 24th of June, when there was a magenta day being highlighted on the strip chart at the bottom. And we can see that was due to the afternoon temperature reaching all-time, very near the all-time record, as shown by the red dot amongst the very highest daily maximum temperature record dots, those gray dots. You can easily see the period where heat risk would have recommended products, or for the meteorologist to consider a product or enhanced messaging as well. So we know a lot of these plots are complicated. They do provide a wealth of information for you to look at and learn how heat risk perform for notable events in your area. You can also utilize the information to work with partners as you familiarize them with climatological heat risk thresholds and provide them with those output at the station level for events that they may have of interest. These annual plots are updated weekly, so you can get quick access after an event. Another cool feature on a historical heat risk page are these station-based daily plot maps that you see on the far left. You can pick any day since 2005 in the pull-down menu and see the observed point-based heat risk output plotted spatially. You can also add a layer of the Wawa heat products that were issued on that date. This is another great way to explore past heat events. Additionally, the data at each of these points are available for partners and you to work towards linking their unique impact data sets to the climatology of heat risk at a station, as we showed a few slides ago. You currently need to request the daily data for a station, but we hope to work on an automated method for retrieving these data in the future. All right, so to wrap up my section, I'll provide you with a few examples from last summer of some heat events over Eastern region, as highlighted by the heat risk approach forced by NBM Day 1 data. While it wasn't an overly hot summer in the East, there were a few periods of enhanced heat events based on the 95th percentile approach that we use, including an event in mid-August where 95th percentile temperatures above the CDC-informed thresholds occurred over a 2 to 3 day continuous period over the Carolinas, which resulted in those magenta areas. While the temperatures were just a bit too warm in the NBM data when compared to station observations, this should give you an idea of how heat risk looks spatially during events such as this. With that, I'm going to hand it over to Kim.
Thanks, Mike. So heat risk has been baselined in AWIPS 23.2.1-46, and we expect all WFOs in the CONUS to have the baseline version installed by the end of May. No more than 2 weeks after the -46 install. And WFOs should be starting to produce heat risk on a cron and sending it to NDFD. So in addition to the viewer that Mike was showing earlier, it will be available on NDFD. So heat risk grids are generated locally in GFE using MaxT and MinT grids from the forecast database. And this is done daily on a cron at 1208Z, which also populates the red, orange, and yellow daily threshold levels. In order to calculate heat risk manually, meteorologists can run the heat risk _calculate procedure under the populate menu in GFE. For offices that are using Forecast Builder, they can set the option to run heat risk to true in their forecast builder config, which will calculate heat risk during the integrity step. And the official rollout of heat risk is April 22nd, Earth Day. There's going to be a press conference. There's going to be a press release, a PNS or public information statement noting a public comment period, social media posts from Weather Service Headquarters account, and a webinar with our partners at CDC. This also means that we'll be directing users to a new viewer on April 22nd. But before I get to that, I want to mention that we will also have a survey for our offices to provide feedback on how you're using heat risk, additional training needs, how your partners are finding it, etc. And we'll be sending out that survey after all the offices have installed and set up heat risk with AWIPS build. So as I mentioned earlier, we have a new viewer. This viewer and also the URLs that Mike had shown previously with historical are embargoed until April 22nd. So, you can share it in your office, you can share it within Weather Service, but please do not share it yet with your partners until April 22nd. I want to say thanks to the Western Region developers and WPC on this CONUS viewer. It's an interactive web page that provides a way for you to look at heat risk live data, and as the animation shows, you can move through the 7-day forecast and then click on a location. You can also, of course, zoom in and zoom out, but when you click on a location, you get that pop-up box, and each of the days has that day's heat risk category. And at the top, there's a bunch of links to PDFs that just have more information on understanding heat risk and understanding the categories, as well as some appropriate actions to recommend with each of those categories. So again, just embargoing that until the April 22nd press conference. And additionally, as I mentioned earlier, by the end of May, heat risk grids will be available for all CONUS on NDFD. And the Heat Risk VLab site also has a wealth of information. You'll be able to access the plots on the historical website, along with additional information about heat risk itself. And in addition, the VLab site contains training materials, weather story templates, outreach materials, and more. And we also have a Google site. You can go directly to the extreme heat section of the site by following the URL at the top, or from our main page, you go to the hazards pull down menu, and at the top, you select extreme heat. We have recorded webinars and training, resources for the rollout of heat risk, as well as materials and resources for heat index, wet bulb globe temperature, pediatric vehicular heat stroke, heat safety, and more. So for our external resources, you can point partners to our safety page. So it's weather.gov/safety/heat index. That specifically leads you to the tools. And this will provide you an overview of the 3 Weather Service tools, including resources and materials such as reference sheets. So lastly, I want to say that heat risk has many advantages. It displays the spectrum of heat impacts, and at least helps start to communicate there's a spectrum when it comes to heat. But it's not the only tool in the toolbox. We have heat index and wet bulb globe, and they are still used by our partners, decision makers, and general public to varying degrees. There's no silver bullet when it comes to heat. So all of these tools should and can help inform you and your partners on how to communicate heat, be it social media posts or IDSS briefings or watch warning decision making. So each of these 3 tools plays an important role in communicating heat, as do maximum and minimum temperatures. And adding heat risk into the toolbox is just part of our unified heat strategy for Weather Service, with the specific focus of intelligent optimization of heat tools directed towards their most appropriate use. So in other words, heat index, that is our flagship product. That is what general public at least has some idea that when you have heat and you have humidity, it makes conditions worse. Wet bulb globe temperature, I want to just remind people that is designed for healthy, active outdoor individuals or communities. So it's kind of another end of the spectrum for compared to heat risk, which really does take into account those who are more vulnerable at higher risk, such as the unhoused, those without access to adequate cooling, air conditioning, and hydration, those with medical conditions, older adults, as well as those who are younger. And last but not least, on the next slide, I just want to recognize all the folks listed on this page for their immense work, their Herculean effort dedicated towards making heat risk what it is today. And thank you for listening. We will open up to questions.
All right, Kim and Michael, thank you so much this morning for this really great, in-depth, and very comprehensive presentation. If you didn't already understand the HeatRisk product and all that it offers you, hopefully you have a better idea of that now and then some. As Kim mentioned, we'll open it now to all of you in the field if you have questions and concerns. Frank, kick it off.
Okay. First of all, I'm glad you put all those names on the screen. I remember seeing this information several years ago, first popping up on Western Region web pages, and I was somewhat concerned about how it would translate, but it's clear that the team has made a significant effort to make this a national product, so I thank you all for that. I do have a couple of questions, though. The first one is, I noticed, of course, we're talking about publishing it on the NDFD site and the web page. I could see this potentially producing another collaboration issue. Is this going to be all done just at one time when the cron is run, or do different offices publish to these sources at different times? How is that going to work to make sure that we're collaborated? And then the second question I had is, obviously there's going to be times where your heat risk is going to show something maybe different, at least in some respects, from the other tools that folks are used to. In those situations, I'm sure they've popped up in the offices that already use it. How have you been adjusting your messaging to let folks know, hey, I understand this looks this color on this product, but not on this product? How have they dealt with those differences?
Thanks, Frank. So I'll mention briefly on the differences, and then I'll pass it over to Mike because he can talk about the experiences that they've had in Western Region. But with regard to the idea of heat index is saying one thing, wet bulb globe temperature is saying another thing, and heat risk is saying yet another thing. They all have their niche, right? Like I said with wet bulb globe temperature earlier, that is really designed for healthy individuals who are doing rigorous activity outdoors. So you wouldn't necessarily want to use wet bulb globe temperature as your only messaging mechanism. And heat risk can certainly help inform some of that messaging overall on how bad the heat is, because it actually takes into account climatology, which both, unless you've run your own local climatology across the year, is not readily available for heat index and wet bulb globe temperature. Mike, I'll hand it over to you.
Yeah, thank Frank for the kind words and also for the questions. So in Western Region, one of the things that we had to work on initially was this desire from the Mets to go back and forth and try to change heat risk. They'd start changing the temperatures and they want to edit heat risk and all that kind of stuff. Heat risk is a non-editable grid. It falls out of your temperature. So if your temperatures are coordinated, then heat risk is automatically going to be coordinated. When we see seams is when offices don't play well with their borders or whatever. With regard to populating the NDFD, that we're just going to have to see how that goes. It is true that as offices, especially on day one, some offices update day one, increase the max temperature a degree or two, passing it over to the red versus the orange threshold it used to be at. You probably will start to see some discontinuities with regard to that. We're just going to have to play it by ear and see what. And again, that is a result of the temperatures that were edited not being coordinated across CWA borders with that update. So I will keep going back to the fact that if the temperatures are coordinated, heat risk will be by default coordinated.
Thank you, guys. Appreciate the effort. Great presentation.
Thanks, Frank. Good to see you.
Thank you, Frank, for the questions. Any other questions, musings, concerns, thoughts? Yeah, Andy, go ahead.
Yeah, I guess I'm just for clarification. So the WPC website that's got the heat risk, it's up and running now. How is that different than the NDFD? I mean, so there's going to be the NDFD here, and then there's going to be WPC, right?
Right. So Andy, WPC is taking the maximum temperatures from NDFD, which are, the WFO generated maximum temperatures, and running the algorithm outside, plotting it onto a map. This actually, maybe getting a little too into the weeds, this is actually an effort that we were trying to do last year when we learned that we weren't going to be able to move forward with heat risk in 2023. And it's just taken, that whole time for them to create a CONUS viewer. Now, the reason you might be asking of, well, if what WPC is already doing this, why are we doing this for WFOs? One is that by having the WFOs generate heat risk, we will be able to get it onto the actual NDFD site. Both the like CONUS viewer as well as the graphical.weather.gov site. And then of course, WFOs will be able to see what heat risk is coming out, become more familiar with it, be able to create IDSS graphics or social media graphics. So it having both, while maybe a little confusing, should at least allow for more flexibility with the messaging. And because WPC is using NDFD, they should be showing the same values. And okay. Mike, go ahead.
I was going to say, you anticipated my second question, the follow-up.
Yeah.
So thank you.
Yeah, thanks for the question, Andy. The other thing I want to mention is that heat risk was designed to be a service. It was not designed to replace Wawa. It wasn't designed to replace Heat Index. It was designed to be a service that people can go to and access the information that they want out through 7 days at the timescales they want. Click their location, get the 7-day forecast, find out how it's verifying, see annual charts and all that, working with the office or whatever. So NDFD doesn't allow for any of that stuff. And frankly, how many people download NDFD grids? We provide GeoTIFFs and KML files that the media have asked for, that the partners have asked for, the graphics and everything like that. NDFD just isn't a very visually pleasing part of it. So NDFD plus the heat risk page in itself is the full service of heat risk in a variety of outputs and user experiences, essentially.
Great questions being asked so far. Let's see, another question came in chat. Could heat risk be used as a recommender in hazard services similar to river flooding and HS?
Could be, right? Yeah, right, Kim?
Yeah, I mean, down the road, with the exception of Western Region, because they've had heat risk for so long, heat risk for the rest of the CONUS being experimental, you shouldn't be relying on an experimental product for your solely on that for your watch warning decision making. But yeah, down the road, it's not out of the realm of possibility.
Yeah, and just in Western Region, the chiclet map that we have for the detailed hazards for heat, in Western Region, we drive it with heat risk, and it's possible that also that could be, inferred by the heat risk product as well down the road as we learn more about it.
All right, we're getting to the top of the hour here, so I'm going to offer another opportunity for any final questions from folks. Mike, did you want to add something final there?
I was just gonna say I could stay on after if someone had a question they didn't want to pose in front of everyone and on the recording. So I got a few minutes to stay after.
Very good.
And Jordan, I'll just plug that we have a recorded training module that's available on the VLab page, on the public program Google Sites, and in CLC, if people want to review that in addition to this recording. And hopefully they have reviewed it already if they joined today.
Perfect. If you actually have a link to that page, you could share it available in chat. That might be ideal. In the meantime, I will mention a couple of details. So one, as Kim mentioned at the beginning of this recording, it was this webinar. This webinar was recorded. We will have that available within the next couple of days as it becomes available. Also, with permission, we'll get the slides up. Thank you, Kim, for the link. We'll get those slides as well, so you have access to all the links and all this information, and a great presentation. Thank you so much for Mike, to you, being with us this morning to present all this information. It's a lot to take in, a lot to process, to say the very least. But we're moving forward, and more information will come nationally as this is rolled out. Any final thoughts, Mike or Kim?
Thanks for the opportunity.
Yeah,
Very-
just thanks to everyone.
Very welcome. So with that said, wishing everyone a good, hopefully a smooth rest of your Thursday, an active weather day. So thank you so much. We'll talk to everyone soon.